All right. Hello, all you wonderful people. Thank you for being here. Let's go ahead and start with what we're doing. So I'm going to tell you a couple of things we're going to do different this week. So I decided to change up my packet. So the homework packets will include some different things in them. One of the things that is different is that the packet is now follow along. So there are two parts to each lesson. The first lesson we're going to be working with is going to be real numbers. So I'm going to start from the beginning, and it looks something like that. So if you have your packet, hopefully you picked it up on Friday or Monday. We're going to be going over this page here that has the bubble diagram on it, the Venn diagram. We're going to go over these first. I think there's about 20 of them, 20 problems, 28, but we're probably only going to go to 24 today. So that first part is going to be the in-class work. That is the part that you will turn in for attendance. The second part is the exact same lesson, but is longer. And that will be the portion you will turn in for homework and your points part of the main points of the thing. So if you come to the lectures or if you do the Zoom meetings, then you will get half of your work done for you. I think that's a pretty good compromise to try and get people to engage in the Zoom and YouTube videos. So I think it's gonna work out a little bit better. So let's go ahead, and before we start, I always like to, if you remember my classes, I usually like to start with something that's a little bit on the funny or the edgy side. Okay, don't worry, you'll get this joke by the end of the lesson. And some other things that you will get by the end of the lesson is to classify real numbers. So you're gonna kind of learn what real numbers are, what they do, and identify and apply real numbers is what it should say, but I guess that's a typo. And apply the properties of those real numbers to evaluate expressions. So that's what we should be able to do by the end of this lesson. So let's go ahead and do a quick recap on what some of these are. So I'm sure you've done this lesson. I know that if you were in Algebra 1, you may have covered some of these. So we're just going to do this part really just quickly. What are natural numbers? So if I asked you to give me an example of a natural number, what would that be? Okay, you probably have a couple of examples in your head, and they probably are right. But a natural number is a number in a way that occurs naturally. So if you think of rocks or sticks, right? Rocks or sticks occur in nature. You can have one rock, you can pick up 2 rocks or 3 rocks, but you cannot pick up a half a rock. If you were to break a rock in half, you would end up with 2 smaller rocks instead of half rocks. So there you go. And also, you know, if you're thinking of things in nature, let's say you have a chipmunk or a squirrel, and you know, you tell him, I am going to give you an acorn. He understands, well, assuming he could speak, he would understand what you're talking about. You could tell him, I will give you 3 acorns. But if you were to tell him, I will give you 0 acorns, that won't make sense to him. So the lowest natural number is 1. 1 is the lowest natural number, and from there it counts upwards. So 1, 2, 3, 4, 5, and I'm going to put some ellipses. That's these 3 dots here. Those 3 dots means that it goes on in that order. So it continues on. So even though it only stops at 5 on our list, it will continue to 6, 7, 8, 9, 10, on and on and on to infinity. Those are the natural numbers. Now, very similar to natural number are whole numbers. Whole numbers are numbers that do not have a fraction or a decimal. So there are no small portions of numbers. There is only whole numbers. So again, they're kind of like natural numbers with only one difference. Whole numbers include the set 0. They include the number 0, but also include the set of natural numbers. So from 0, 1, 2, 3, 4, 5, and so on. So there we go. 1, 2, 3, 0, 1, 2, 3, 4, 5. Those are the whole numbers. Now, why is 0 considered a whole number? Well, it's not 0.2 or 0.5. So if it does not have a fraction or a decimal, then it is considered a whole number. Because that's kind of what whole means, right? It means you have the whole thing, not extras or you're short of it. So that's a quick recap on natural and whole numbers. Now, if you look at the packet that you're supposed to be following along with, you will notice that it does not go over these numbers here that we are going over right now. And like I said, most of these numbers you've been using for a very long time, and this is just really a refresher. But I'm kind of going in the opposite direction that the packet is going in. I'm going to start with the easy numbers and kind of work to the more difficult ones to understand. The next ones are integers. So integers, continuing on, we have a number line. All right, so this number line is pretty interesting. It goes from the numbers we covered, so the natural and the whole number, so it starts from 0. And then if we go to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it will go on and on forever. Now, I was at my sister's birthday party about 2 weeks ago. And I guess there's this stigma about turning 30. You know, people for some reason really don't like turning 30. So she goes, I'm going to be 29 a whole nother year. Okay, that's not how it works. And then I joked and said, you know what, I'm going to just skip a year and just go to the next year. So just to give you an idea, that's like if you were 16, all right, some of you guys are probably 16 or 17, whatever. But let's just say you're 16 years old. You can't just be 16 and then go into 18. That doesn't work that way. So this number line contains no jumps, gaps, or anything else. It's just equal numbers from one to the next. So 1, 2, 3, all equal spaced. So again, we also call these sides the positive numbers, which again, those are the natural numbers or same thing as positive numbers. But then we add an entire new set of numbers when we go to the left. When we go to the left, we end up with negative numbers. And they too are equally spaced, no holes, no jumps, no gaps, and it does go on to negative infinity. So it's kind of like having an evil twin for every single number that you can think of. So if you thought 1 to infinity was a lot, well, try a whole nother set of infinities. So there you go. That's the positives, negatives, and we also have a third number among the integers, and that is 0. So 0 is not positive, nor is it negative. So 0 is neither one of those numbers. 0 is its own category. All right, there is no such thing as negative 0. It's the same number. 0 is 0. And that's pretty much what we have. So positives and negatives. So sometimes we refer to a number as its opposite. So what an opposite means is if you have, say, 6, right? If I look at the distance from 0 to 6 and go in the opposite direction, so I'm going to go this way, and I went that exact same distance, I would end up at negative 6. So therefore, the opposite of 6 is negative 6. Okay, now I know probably by the time you were in junior high school, you may have uncovered integers. And when you first heard about them, it may have been weird or mind-blowing to think about it. Because again, you can't have negative rocks, so why do we have negative numbers? Well, there's a lot of things in life every day that are just arbitrary. Like money is one. You can have negative money. So I know most of you guys are a little bit too young to know this, and I know even fewer and fewer people watch game shows. But back in the day, before reality television, game shows were what used to show during the day when you had to stay home or whatever. So in Jeopardy, if you get a question right, you get the positive value of that question's money, the money value. You would get a positive. So you'd say a category for 400, you answer right, you get 400. But if you get it wrong, you lose $400. And as you can see in this picture here, I have some people that have a negative balance on their winnings. Now, I'm not really sure how that played into the game. I don't know if they actually owed money or something, or if it was just zero. But it's just like a bank account. If you draw more money than you have, then you get an overdraft, and you end up having to pay a fee or something like that. So you got to be careful with that. Another place that you may encounter negative numbers would be temperature. So the coldest temperature in an area was -4 degrees. Now I remember this one because I had a student a long time ago when I talked about -4 degrees. She was like, "Oh no, wouldn't you just die if that happened?" And I thought that was just the funniest thing. Like if it's snowing outside and you walk out and then you I don't know, you just like die. That's it. No, if you've seen snow, chances are then it was below freezing, right? Because 0 degrees is where water freezes. All right, so snow can stick around a little bit higher temperatures than that, but again, usually if it snows, it will oftentimes get below 0. Some other places would be altitude. So if I were to ask you how, because you know that certain areas are higher and lower, like for instance, Flagstaff is higher in elevation and Phoenix is lower in elevation. And a lot of times you can easily feel that, you can, like if you're driving to Phoenix, it just slowly gets hotter and hotter if you were, had the windows rolled down or something. Well, that's because if you have a beach, you are at sea level. So here's a beach and there's the water coming in, and that is right at sea level. So when people talk about altitude, they're talking about sea level. But in this case here, we have a valley that is well below where the sea is. So it actually has a negative altitude. And that place is Death Valley, which is extremely hot. It's even hotter than Phoenix, and you thought Phoenix was hot. It's like in Phoenix, when you get out of the car after the air conditioner's on, you're like, oh my God, it's like standing on the sun. Why do people live here? But anyway, that's one example of where you can have a negative altitude. So it would be -227 feet. Also, rocket launches are counted from the negative time. So like they may say T minus this many seconds. And the reason they do that too is because it goes from time to launch. In space, night and day have no meaning, because if you are running circles around the Earth, daytime is whenever you see the sun, and nighttime is whenever you are in the shade of the Earth. So you are practically always going into night and day several times a night and day. So what are rational numbers? So we covered integers. So what you do is you take an integer. So in this case here, let me just use this first example here. I have 2. I have taken the integer 2 and I'm going to divide it by 3. New number, all right? Take one number, take another number, divide them, and you get a whole new series of numbers. Now when you divide them, you end up with portions of a number, numbers between numbers. So like for instance, if I were to punch in a calculator 2/3, I would get 0.666 repeat. And that is somewhere between 0 and somewhere between 1. So it's not an integer and it's not a whole number. But if you look at your packet, it is defined as can be a fraction. So that's kind of the test that you can give yourself for finding out whether a number is rational, is that it can be written as a fraction. Now, just because it can be a fraction does not necessarily mean it will be a fraction. So like, for instance, you might be looking at this number here. These are all examples of rational numbers, and you might be looking at 4 and go, well, that's not a fraction. Oh, but it is. If you remember working with fractions, when we had to add or multiply them, I would sometimes tell you, put a 1 under it to turn it into a fraction. There you go. Now 4 is a fraction. The same can be done with -3, and 0 is also a fraction because you can put numbers under 0. -23/8 is also a fraction, although this is an improper fraction where we have a top number that is bigger than the bottom number. Or you could also, again, have numbers between numbers. So 2.4 on the number line is between 2 and 4. This can also be written as a fraction, 0.17. If I wanted to write that as a fraction, I could put 17/100, because in both cases you would say -17 hundredths, -17 hundredths. And this also includes what we call mixed numbers. Mixed numbers have elements of whole numbers and fractions. Now, we could also change this 23/8 into a mixed number as well. And the official definition, I'm not sure if it says this on the packet, but the official definition of a rational number is a number a over b, or a divided by b, where a and b are integers and b cannot be 0. Now, something weird happens when 0 is on the bottom, but that's not really part of it. But, you know, try that on a calculator one day and see what happens. Now, for this one here, I'm going to go ahead and go into just a quick example of one pattern of behavior that rational numbers have. So for this one here, just try to remember the numbers 5/8 and 7/11. So with this one, I am going to need a calculator. So I'm going to switch over to calculator right now. Okay, I think you can see it. So I'm going to type in 5 divided by 8. And I get 0.625. Now this number stops. It only has 3 numbers after the decimal point. So by having 3 numbers past the decimal point, it's what we call a terminating number. Terminating, okay, I know sometimes you might be thinking of futuristic robots, but really terminating just means to end. So this number ends. Now let's look at the other number in that example, 7/11. Now in this case, something else happens. We get 0.636363636 on and on and on, just like that. It goes on and on practically forever. Now I know you're probably looking at that 4 saying, well, hold on a minute, doesn't that break the pattern? Well, not really, because they rounded it off. This calculator can only show 30 decimal places, and it just rounded that last number off. So the next number after that would be 3, but the number off screen would be 6, so they rounded it off. So since I got better things to do than to write repeating numbers for the rest of my life, you know, I have to pet animals at some point. I'm gonna shorthand it as putting this little repeat bar over the top. Now, when you have the repeat bar, in this case, it has to be over 6 and 3 because both 6 and 3 are repeating, because it's going 6, 3, 6, 3, 6, 3. If you have that repeat bar only over one number, then that's the only number that repeats. Now, these 2 numbers are still rational, and you can think of it in 2 ways. Rational people, all right, so think of it like something that people would do. A rational person is somebody who thinks clearly, who thinks predictably, right? If somebody is rational, you can almost predict what they are going to do, which is usually not something crazy. In this case here, even though 0.63 repeats, it is still predictable. I know what's going to happen next. I can easily predict it from where I am. This one ends, so it's predictable. We know that it's going to end. So these are still rational numbers. Let's get into what is not a rational number. Some numbers that are irrational. Ir meaning not, so not rational. So just like irrational people, they're tough to predict. So let's go ahead and look at these 3 upper examples, root 3, root -8, and root 11. Now for this one, I'm only going to use 2 of them. And let's go ahead and do that. So I'm going to take the square root of 3. So there's 3 and square root it. I have 1.732050807 5, 6, 8, 8, 7, 7, 2, 9, and so on, right? I have all these numbers. And okay, you can calculate them, but from where we are now, it becomes really difficult to predict what number will come next. This number goes on and on and on. All right? It never ends. It just keeps going. And again, it seems kind of random, like an irrational person. Let's try another one. The other example that I wanted to go over was 11. So square root of 11, same thing. Now this calculator has 30 places of digits. So let's try 0.316. If in 30 numbers, it should show up at some point what we can do. So let's see, 316, 316, 316. So at some point, if I see a 316 again, then that would mean it might repeat, but it doesn't. There is no more 316. If I had 100 decimal places showing, it would still not repeat itself. So that is how you can tell what an irrational number is. Now let's go ahead and start with another one. Now, since we were working with radicals for the past few weeks, you will probably know what the square root of 16 is, and you get a whole number. This whole number is not, it does not terminate. I mean, it does terminate. It does not terminate was what I was trying to say. And it does not, well, it's rational. Sorry, I'm twisting up my own words now. But we know that this is just 4. We know the square root is 4, which is a whole number. And we don't get any weird decimals, basically. So we know that that's what it is. Now, if you look at your packet, that has a much different definition. I also noticed that I think let me see. Numbers in which, so an irrational, now it has a little bit backwards, but again, I'm covering them in order, a specific order. But a rational number is the number in which the decimal form either terminates or repeats, and rational numbers can always be written as a fraction, which again doesn't mean they have to be a fraction, it just means they can be written as a fraction. And irrational numbers are numbers in which the decimal form never terminates and does not repeat. So common examples are, now it's supposed to say pi. Common examples are pi and the roots of non-perfect square numbers. Now, I think when I transferred the text, I think the pi didn't show up. But there is supposed to be a pi in there. So that's what it means by the non-perfect square numbers, the roots of non-perfect square numbers. So if you remember that last slide, when we took the root of 16, it was rational because 16 is a perfect square number. Perfect square numbers are the numbers where you multiply two numbers of the same kind to get a new number. So those are numbers like 4, 9, 16, 25, 36, 49, 64, and so on. So anything that is not on that list.
In the building, call extension 1039, or in the laughter, call 1039.
So anything that is not on that list, like if I take the square root of 60, then it will result in an irrational number. So there you go. That is the definition of both of them. And again, this one's on your packet. And it's probably a little bit more accurate because it does not have the pi missing from it. So the next part, and this is the part where we begin working on the packet. So if you have your packet in front of you, that will be this page here. So you can already see the diagram, a little bit higher, there we go. So you can see the diagram and it's asking for a letter and some examples. So you can fill this part in along with it. So that will cover your in-class work portion of the assignment. Or if you can't watch this video in person, then you should go to the channel and watch the video there, and you will still get the examples to cover for the in-class work. So this one's kind of a weird one because I remember learning something a little bit different on this one. Irrationals used to be Z, if I remember correctly. I knew there was a Z somewhere in there, but I'm working with the material I have now. And sometimes they're a little bit weird. Like for instance, integer and irrational both start with I, so we had different letters for them. So watch out for that. So you're gonna want to put that in that first column that says letter. So one other thing I'm gonna point out with this diagram, well, this is actually a Venn diagram where certain groups can belong inside other groups, or what we call sharing elements. So an example, let's just pick number 2. So number 2 is a natural number. And because it is inside of these, it is also those groups as well. It belongs to those groups of numbers as well. So 2 is a whole number, 2 is an integer, 2 is rational, and it is also a real number as well. But you can pick some that don't match. So we know 2 can be an integer. Let's try this example that it gives us here, -3. And you can also use these examples for the examples over on the column that says examples. So -3 is what they give us as an example for an integer. Now, -3 is an integer, it is rational, and it is real. But it is not a whole number, and -3 is not a natural number. So some parts, some numbers can belong to elements above them or below them, but every number, it belongs to the group that is also inside of that same bubble too. Like for instance, 2/3 is a fraction, which makes it rational, but it is not an integer. Even though this number is negative, it is not an integer. So hopefully that kind of clears things up a bit. So again, 0 it belongs to all of these groups except natural numbers. And then you kind of have the group over here all by itself, the irrationals. All right, so that's the only group that's somewhere outside the main group. There's also imaginary numbers too, which are the only things that are not part of the real number set. I think there's a few others, but like there's the undefined that is not part of the real numbers. So here are some more examples if you want to. You can take some notes on this part here. Now this is a lot of examples to go over. Maybe I'll just go over a few on each one of them. But again, there's the letters that you're supposed to put into those groups. And then you also label the diagram that you see, which is a little bit backwards than the one I showed you on the previous screen. But again, there we go. So they're all labeled. So like pi, again, if you see the word, the letter pi, or I should say the variable pi, we use it oftentimes in calculating things with circles, like circumference or area of a circle. And a lot of times we just approximate that to 3.14. Although if you look at the actual digits of pi, it's 31415926535897993 23846243, something like that. But it goes on and on forever. So yeah, it doesn't really repeat in any predictable manner. Now it's not to say it's random, by the way. Don't confuse that with random. Every time you type in pi, it always means the exact same number. But I'm just saying that the decimals generated as you go lower into the place values seem random. And anything that is the root of a non-square number or non-perfect square number, those are always going to be irrational. And rational numbers. So again, even though it's a decimal, it can be written as a fraction, and that includes mixed numbers, repeating decimals, and both of these are repeating decimals, or numbers that can be written as fractions. Integers. So integers are whole numbers. Now this first one might look a little bit weird. Now I want to point this out because -100, you might be thinking, well, wouldn't that be irrational because there's a radical? No, because if we evaluate 100, as we take the square root of 100, we get 10. So after we use up the radical, it just becomes 10, and 10 is a regular number. Well, actually it's -10 because that negative is still in the front of it. And this number is a fraction, and you might be thinking, well, isn't that rational? Well, not necessarily, because if we evaluate 8 over 4, which is 8 divided by 4, we get 2, and 2 is a whole number and an integer. And the same thing with these whole numbers too. So if we evaluate some of these, we get whole numbers. With some of these, if we evaluate these, we get natural numbers like square root of 9. If we take the square root of 9, that is the value of 3. So even though they look kind of weird, be careful. You got to look at them a little bit more closely, evaluate them if you have to. One really good thing about this packet is that since you're following along, the examples are already on the page. So you don't have to worry too much about copying notes or getting any of that stuff in your notebook or anything like that. So I guess if you, well, I don't know how we could do this. Maybe you could make a copy of it or something. I don't know. And use that as your notebook. I used to do that at my old job. I used to work at a different school, and that's what I used to do. Is I used to have like a separate set of exercises that would be in the notebook that would also include things like definitions and fill in the blanks for definitions. But you know, I'm working with what I have. So what we're going to do with these is we are going to look at these numbers in each exercise and name the sets to which all of them belong. So some of them are different numbers. And again, we still have the numbers up in the upper corner of this screen. So let's look at this first one, -10. So -10. So what you could do is start from the top, like natural numbers, and work your way down. So -10 is not natural. It is not whole. It is an integer. So let's go ahead and put the mark for integer. So I. It is rational. So let's go ahead and put Q. Now again, this is a little bit weird because like you might be thinking rational. Well, shouldn't that be R? But again, real number is also R, which all of these are real numbers on this exercise. So don't worry about putting real number on there. As long as it's not imaginary or undefined, then it is a real number. But we're kind of done with imaginary numbers for now. So let's go ahead and move on to exercise number 2, square root of 30. So 30, let's see, is it a square?
Tell Curly to the front office. Tell Curly to the front office.
Is 30 a square number? Well, no, because 5 times 5 is 25 and 6 times 6 is 36. And there are no numbers in between that we could square to get a number like 30. So that would make this irrational. So we put a P to mark it as irrational. Now for exercise number 3, this is a mixed number. Now again, if you were looking at the notes that were not in the packet, one of the examples that I told you, actually, or I also put it on here as well. So if you were filling in the area from here, then you would also know that mixed numbers are counted as rational. So it is a rational number. Now it is not an integer, it is not a whole number or a natural number, so it only belongs to this group. You could also put it into real numbers, but again, all of these should be real numbers, so don't worry too much about that part. Now, here's where I told you to be careful of some of these tricks. Anytime it has an operation in there, let's see if we can do that operation. So can I divide 24 by 8? Yeah, and you know, does it become a decimal number or a fraction or a mixed number? No, it becomes 3. 24 divided by 8 is 3, so this is just 3. So 3 is natural, it is whole, it is an integer, and it is rational, sorry. So it is all 4 of those groups. Okay, well, what about 2.48? Now again, decimal numbers that terminate, which this one terminates, it only has 2 spaces and then it stops. So that would make it rational. And again, I could also write it as 2 and 48 over 100. Now I know most of you guys are, shoot, this was something a long time ago, but back in college, I used to pay my rent with checkbooks, and that was like a long time ago. Nowadays, I think even fewer people use checkbooks. But I remember when people used to write checkbooks, like say in this example, if they wanted to write 48 cents, they wouldn't necessarily put 0.48. They would put 48 over 100, and that would be how they would write cents, because you're talking about a portion of a dollar. But again, nobody does that. Nobody uses checkbooks, and so we kind of lose our fractions a little bit in that regard. Anyway, let's move on to number 6. So we have the square root of 81. Now there's a negative, but I'm going to ignore that for now. Now be careful, because sometimes when you see a negative on a radical, you might be thinking, well, won't we get an imaginary number? No, we won't, because in this case here, negative, and if I take, the negative is on the outside. Remember, imaginary numbers only count when the negative is on the inside. So if I were to take the root, if I evaluate the root of 81, I get 9. So in this case, the actual number, the actual value is -9. So what group does -9 belong to? Well, it is an integer because it's negative. It's not a whole number, it's not natural, but it is rational because it can be written as a fraction. And it is also a real number, but again, I'm not going to put real number on all of these because that would just be quite a bit of work. And number 7. Now this one's a little bit tricky because you might be looking at it and saying, well, pi, isn't pi irrational? Now this one kind of fits with a number property. And by number property, I mean something that numbers do all the time in a way that is repeatable and you can make shortcuts with it. So this is a property known as inverse, and that means if we take any number and subtract that exact same number, we end up with 0. So even though we have 3.14 something 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 minus 3.14 something something something, the actual value of this will be 0. So now we look at what all numbers 0 are. So 0 is a whole number, right? It's not natural, but it is whole. And we work our way down. So whole number, it is an integer, it is rational, and it is a real number. Okay, am I missing one? Somehow I feel like I'm missing one. So let's see, whole, integer, rational. Okay, yeah, that's close enough. And we're done with that one. Let's move on to exercise number 8. Now, if you remember properties of radicals that we covered, you can split this into 2 groups with each of them having their own radical. So if I take root 16 and put it under its own radical, and I do the same thing to 25, well, you can take the square root of 16. That's easy enough. You get 4. Take the square root of 25, you get 5. So now we end up with just a fraction. So even though it had radicals and we might have thought, well, this may be irrational, no, if we evaluate it, then we see that it is just a plain old fraction. And that means that this is going to be, well, it's not an integer, but it is rational and it is a real number. So there we go. All right, number 9, we have a repeating number, 0.15 repeat. Now in this case, if we expand the number, meaning we write all the parts out, 0.151515151515, but it's predictable and it repeats itself. So since it repeats, it's predictable and is therefore rational. And it's also a real number as well. But let's go ahead and move on to number 10, so 109. So this is a natural number because you can have 109 rocks. It can be a whole number. It is an integer because it's positive. It can be written as a fraction, right? 109 over 1. Now again, just because it's not a fraction doesn't mean it can't be written as a fraction. And in this case, it can be written as a fraction. So it is rational. And now I also have 8 over 3, well, negative 8 over 3. So you might be thinking, well, if it's negative, then it might be an integer. But again, integers do not include fractions that are unsimplifiable. So in other words, I cannot divide 8 by 3 and get a whole number. So in this case, it's only rational. Now this next one, number 12, is also a number that is, we're going to cover very soon. It's a property that is, the property of this number is that any number divided by that same number is going to be equal to 1. So even though 7 is an irrational number, if I evaluate this using the property that any number divided by itself equals 1. So in this case here, the actual number is 1, which is natural, it is whole, it is an integer, and it is rational. So it is all of those numbers. So again, try to evaluate these and think, is there anything more that I could do? Is this number trying to trick me into thinking that it is something that it's not necessarily supposed to be? And there we go. So again, be careful, go through them. Let's go ahead and move on to the next type of exercise. Now for this one here, it's probably easier if I just put up the what you're supposed to write here. And this is actually an extension of the first assignment. And this is properties of real numbers. So as I was saying, a number property is something like you can think of it as a shortcut. When something does the same thing over and over again in a predictable manner that is really easy to spot, that's one way you can think of a number property. So like, just an example, the property of rubber is that it bounces. So a lot of toys, like a ball, is made of rubber. That is a property of rubber. So again, it's something that it does over and over again. You know, glass is hardened, but it is not very flexible. You know, metal is bendable. You can bend it with your hands, but you can also bend it back. It is malleable. So that's a property of metal. Okay, so properties of numbers. So on each of these, they give you an example in addition and an example of multiplication. So I'm going to go through them and explain them one by one. So we have the first property, which is commutative. Now I know some people say commutative, but it's commutative because there's two T's. You got to say T twice. And the idea behind commutative property is that you can switch the order of numbers. So in this case, I have A and B is the same thing as B plus A. Now, if we just come up with a really quick example of this one, let's say 5 plus 7, right? If I have 5 plus 7 and 7 plus 5, will they be the same or will they be different? Well, they're going to be the same, right? It didn't matter which one went first. When we add them together, they come out to be the exact same thing. And then you also have this one here, with this, which is multiplication, and it's the same thing. Let's say 3 times 5 and 5 times 3, you will get the same answer. It didn't matter which one goes first. So the thing that makes commutative property commutative is what we call the order. And I don't mean the kind you do at McDonald's. I mean which number goes first. So ordering which one goes first, second, third, or whatever. So the primary thing that makes commutative is the order didn't matter. And this that one is oftentimes confused with the next one, associative. Now, in associative, okay, so let's look at this first example. It says A and B added together in parentheses, so that says do it first, then add it to C. Well, what if I were to do that exact same thing, A, B, C, A, B, C, so that it's the same order. We didn't switch any of the places of any of these numbers, but it's telling us to add B and C first. Now that wouldn't make a difference because we're still adding it to A. All three of these numbers are still being added together. But you might be saying, well, isn't that the same as commutative? But there's one very key difference that you have to be careful of. And in this case here, the key word is the group or groupings. And one way you can kind of tell them apart is to think of it in terms of like the vocabulary. So if I said an association, what's the first thing that comes to your mind? Well, you might be thinking of something like the Homeowners Association or AARP. I can't think of any more examples, well, appropriate examples, I guess, but if you are a member of AARP, you are very likely an old person because you have to be a certain age in order to join the American Association of Retired People. So you, again, if you are part of that group, then you're in that group. So another one is the Homeowners Association. Some neighborhoods, they put the responsibility of the people who live there, they take responsibility for their houses. So they call that the Homeowners Association. So if you live in that neighborhood, chances are you belong to that group, or if you belong to the group, then you definitely live in that neighborhood. But the groupings are what's changing. So even like on this example, if I multiply A times B and then multiply C, it would be the same thing as A times the product of B and C. It wouldn't matter which one I did. They would still be equal. So again, those are the ways you can tell the associative and the commutative property apart from each other. Because I know a lot of people confuse those two. So let's go ahead and go on to the next properties, and the next one is the identity property. So this one's pretty easy. If I had, like, take the money in your pocket, and if I give you $0, now how much money do you have? Okay, it's the same as you had before, right? It didn't change. Same thing happens when you multiply something by 1. It doesn't change the value. So A plus 0 is A, and A times 1 is A. Now in this case, A is any number, so any number plus 0 is still that same number, is kind of the way you would read it. And one way to remember it is identity is who you are. So everybody kind of has a way that they are, right? It's like that person is this way and that person is that way. And there are certain things in life that will cause it to change. Like if you watch a superhero movie, there is often something very drastic that happens to the person, the character, that makes them become a superhero, or in other cases, the supervillain. Now, those are big examples of identity changing. But if you ate a burrito, is your identity going to change? No. No, even if it was a particularly good burrito, it probably still wouldn't change your mind about how you see the world or what kind of actions you do. So it's something small that doesn't really change anything, is the way you would think of identity. And the next one is inverse. So if you remember from that last slide, I had two examples, pi minus pi and root 7 divided by root 7. That's a way of undoing an exercise. So a really quick example of inverse is, let me see if I can just write this out. Let's say I have x minus 8 equals 13. Now, if I wanted to know the value of x, what would be the first thing I would do? Well, we got to get this 8 out of here, right? So I would add 8. Now, by doing the opposite, because this top one, the original, says subtract 8. So if I add 8, which is the opposite, it will undo that number. It undoes. Right? So that's that. You've been using this property for as long as you've been in algebra. The same is true here. If I have an example, like for instance, let's say 5x equals 15. So how would you get rid of that 5 so that we get x by itself? You'd say easy peasy, divide both sides by 5. Now this is a little bit different because rather than dividing it, we would be multiplying it toward the reciprocal of that number. So the reciprocal of a number, like if I were to, okay, I already used 5, so let me come up with a different example. Let's say 9. If I had an example of 9 and I want to multiply it to get rid of it, I would go times 1 over 9. I would just take that number and flip it. By doing that, I end up with 9 over 9. And if I divide 9 by 9, I get 1. So now this is the only property that's really different between the two of them, is that inverse, you have to go back to 0, and with multiplication, you have to go back to 1. And again, this is a property that you use all the time, because if you take 5 divided by 5, that will cancel out, leaving x by itself. Well, not really by itself, because 5 divided by 5 is 1, and 1 times anything is that same number. So you've already used identity property and inverse property in one problem. And again, you've been using this your entire life. You just never knew it, probably never knew it. And the last one is distributive. Now, again, I know of very few students that reach me that don't know distributive, because in junior high, it is just drilled. So you know what it is. And it's oftentimes explained as multiplying both numbers inside the group by the outside number. So in this case, A times B. So, okay, I got A times B right here. And I have A times C, which is A times C right there. So we have both of them multiplied. Now be careful, because distributive can look like associative, because they both have parentheses in them. But again, you got to look a little bit closer, and you got to ask yourself, what are these numbers doing? Which is actually our next exercise, is that we are going to identify what property is being used and classify that property. And again, this one is part of the packet, so don't worry about it. If you haven't received the packet yet, you can always take this video and watch it again to get your answers for this part here. So name that property. Let's look at number 13. So what is going on here with number 13? So maybe it's commutative. Let's look at the order: 5, 2, 8, 5, 2, 8. So both sides have 5, 2, 8 in that order. So the order did not change, so this is not commutative. But if we look at what's actually changed, it's the parentheses. On the first side, they have us multiplying 2 and 8 first. And on the next side, they have us multiplying the 5 and the 2 first. Since the grouping is what changes, and again, an association is a group of people, that means that we are looking at an associative property here. All right, so hopefully you get the idea. And I just put them here so that way I wouldn't have to write them each time. Now let's look at this next one. What's going on with this one? Is this one associative also? Be careful, because I told you, just because it has parentheses doesn't mean it's going to necessarily be an associative property. So let's look at it. 6 times 3, right? So we multiply it to the first number in the group and the second number. 6 times -7, or 6 times 7, right there, 6 times 7 again. So that means that in this case, it is a distributive property, because we distribute that 6 to both numbers on the inside of the group. Okay, not bad. Let's go to number 15. 7y plus -7y equals 0. So again, like in algebra, if you have a 7y and you want to move it to the other side, you would have to minus 7y from both sides. That's not anything really new. That would be inverse property, right? Because again, we're doing, I don't want to say that, okay, because again, opposite can mean something. We've already covered what it means in integers. But when you think of the word inverse, think of the word backwards or reverse. Inverse just means backwards. So if you add 7y and minus 7y, they're opposite, so they cancel each other out. They're inverses again. I use that word opposite again, even though I wasn't supposed to. All right, number 16, 3a plus 2b equals 2b plus 3a. So what's going on in this set here? Well, 3 and the a are still together, and 2b and 2b are still together on both sides. So we're not really changing any groupings. There's no parentheses. So this is an example of commutative. We just switch the order of the numbers, and it should still mean the same thing. And there you go, we're done with that one. Let's move on to number 17. So look at the order. Whenever you see these adding or multiplying ones, just check them. Make sure that they have the same order. So x squared, 8x, 1. X squared, 8x, 1. So this is not commutative. But if we look at it again, the parentheses are changing which set they're on in both of them. So this is an example of associative property because again, the group is changing. Or like if you have friends, you may call them your associates because they are part of your group. Okay, now we have another one, our inverse property. Now again, you multiply the reciprocals. So like in this case, we have 5 and multiply it by 1/5. Now, some countries do have a 20-cent piece of a coin. So like in America, we don't have such a thing. We only have a 5-cent, 10-cent, and 25-cent pieces commonly. But in some places, let's say that there's a 20-cent piece, you would need 5 of those in order to make that country's dollar, or whatever they call it. So in this case here, if you have 5 of those 20-cent pieces, you have $1. So that is an example of inverse. Now let's look at number 19. Now this one might be confusing at first because you're looking at it saying, okay, well, if we move from left to right, what changed? What happened? What action occurred? But if you look at it backwards, you'll notice that it's just distributive property. Now, if you remember from solving radical equations, sometimes you have to factor them. And that's exactly what's going on. With distributive property, you're giving numbers, whereas with factoring, you're taking numbers. So even though this is technically factoring, we are also distributing. Those two things are inverses of each other. Factoring and distributing are inverses. They're the backwards and forwards. It's the same car going forward or backward. And this last one would probably be pretty easy. Okay, well, if you're looking at the options, you notice there's only one option left, and that is the identity property. Because 9c plus 0 is still 9c. Nothing happened, nothing changed. Its identity is still the same. Okay, it's like if Batman's parents, or he wasn't Batman, his name was actually Bruce Wayne. If his parents were still around, he would still be Bruce Wayne. Well, he still is Bruce Wayne in his heart in here. But he's also known as Batman now because of what happened to him. Which is why, I don't know, I think sometimes superhero movies are overrated like that because it's always like, oh no, this big old thing happened. Which is like why One Punch Man is like probably so good. If you've ever seen it, definitely watch One Punch Man. Like it's just, it's so different because it turns so many superhero tropes on their head because like the guy never had anything happen to him and he just decides, you know, I'm gonna go be a hero. And he does. I mean, it makes for an interesting story, but I don't know if it really helps out all that much. All right, last part of the exercise. So we're still on number properties. Now, what we got to do is we got to get the inverse of each number. Now, if you remember, I used this exact example before where I have x minus 8 equals some number. I forgot what I put on there. But anyway, what would you do to get rid of this is what this exercise is about. So you would probably say, well, if I want to get rid of this minus 8, I would add 8. And that's exactly what you put here. You would add 8 to get rid of it. kind of like if you remember, well, I don't know if this is something that really happens because now modern washing machines and soap are very good. But long time ago, they used to always have like, what do they call them? Home remedies. But it's not really a home remedy. This is before they came up with the word life hack. Like they would say, oh, if you want to get grass stains out of your clothes, kind of like an old wives' tale, I guess is what you might call it too. They would say, oh, use this soap or hit it with this kind of oil or put this food on it and that will take out your grass stains. But I don't think that really happens anymore. I think soap is just so good now. It's just, it doesn't really matter what you do. But that's kind of like that. You have to do a specific set of steps to get rid of it. Okay, now if we had to multiply to get rid of this, let's say we had negative 8x equals 24. What would I have to do to get rid of this negative 8 times x? Now remember, that's negative 8 times x. Well, one thing I could do is times it by 1/8, by negative 1/8 actually, times negative 1/8. Now that timesing it by the reciprocal is the exact same thing as dividing it. So in this case, it says use the multiplicative property, so we have to multiply. And again, multiplication and division are literally the same thing. They're not brothers, they're not cousins or even twins. It's the same car going backwards or forwards. So in this case here, the inverse would be negative 1/8. So that's what I'd have to multiply to get back to 0. Or I'm sorry, 1. I want it to be 1 because 1/8 of 8 is 1, and 1 times x will just give me x. And that's how we would get our answer. Now again, this is just an example. Don't worry about that at all. Let's go ahead and do this one here. So if I had, say, 2/3, how would I get rid of that if I had to add something? Well, you can add negative numbers. Let's see, that 2 is a little bit off. I'm going to kind of use the little slanty slash there. I want to write it big because I know some people might be watching this on a phone or something. So there we go. And in order to get rid of this, now since it's already a fraction, remember if you say if you have a whole number like 8, you would put a 1 under it and then flip it. But if it's already a fraction, you just flip it. So there you go, flip it. Flip it good. I'm kidding. Now, what if it has a variable, huh? What do you do if it has a variable? Well, you do the same thing. If I want to get rid of a 6w, minus 6w. And if you want to get rid of it when you're multiplying it, then you multiply it by 1/6w. You turn it into a fraction and then reciprocal it. In other words, flip it. And there we go. Now I want to get rid of root 10. Now this one's a bit of a tricky one because my first reaction to do this one would be, well, can't we just square it? But we're not trying to get rid, or I'm sorry, we're trying to get rid of the whole thing. We're not trying to get rid of just the radical. So in this case here, if I wanted to add something to it, I would say minus root 10, and it will become 0. Because again, when you're trying to do the additive inverse, you're trying to go make it be equal to 0 so that you can apply identity property to it. And multiplicative is going to, hey, sit back down. The bell doesn't excuse you, I do. Negative, I'm sorry, not negative, but reciprocal root 10 as 1 over root 10. Okay, there we go. We're finished with that one. And we are done with this one. This one, I think, took a little bit longer. It's a pretty big vocabulary and property heavy lesson. So yeah, there are a lot of stuff going on with this one here. So that will be it for our lesson. Let's not worry about this part here. Okay, let's just forget that for now. We'll probably cover it some other day. Or you know what, if I don't get time to cover it, just put attended the lecture on this, and that's free points. Okay, so if you watch the video or if you are here at the lesson, free lesson. All right, I told you, go ahead, just put right down there that you attended the lecture or you watched the video, and that's it. You don't have to do those last few problems. So that's hopefully an incentive for you to watch future videos and future lessons. So that will be it for today. I will hopefully see you guys later.